Thank you. Good morning, everyone. So unlike Pierre, I don't have 40 years of experience, so this is going to be a slightly more conventional talk, just so that you can adjust your expectations. But basically, the motivation for this talk is that, as you know, in this conference, it's becoming easier to collect and analyze a lot of kinds of multimodal data. And in education, this is something really interesting for us because it means that we can focus more on learning processes and a little bit less on learning outcomes like high-stakes tests. And process data offers a lot of benefits potentially in education. If you can figure out what students are struggling with, when they're struggling, if you can see what kind of strategies they're using, that gives you a lot more information to figure out interventions to help them. It also helps you provide more detailed formative feedback. It helps you help teachers manage classrooms and figure out what is going on among their students. But where do you start? As I've seen and experienced over the years, it's easy to get lost in a sea of data among all the different possibilities that you can explore. And in my lab, we've worked with pose data, physiological data, emotion data. And to be honest, most of the time we found pretty mixed results on the value of those data sets. They're actually difficult to make sense of and to make them actionable in actual educational settings. So today, I want to focus on probably what is the most successful application that we found in this field. Instead of talking about all the things that didn't work, today I wanted to talk about one thing that actually seemed to work. So as you guessed from the title, this is going to involve dual eye tracking. And in the first part, I'm going to talk about how does that work, how can you collect and process the data in meaningful ways, what can you say from it, and how does that inform theory about, for example, collaborative learning. In the second part, I want to go beyond just describing what students and groups of students do, and I want to talk about how we can design interventions to actually support them. And that's going to involve an intervention known as a shared gaze visualization. And in the third part, I want to talk about going beyond, using dual eye tracking because they're very bulky and expensive sensors, and it's not something you can use in actual classrooms. So I want to show you a couple of applications and examples of next steps that we're focusing on. So first of all, why dual eye tracking? Was that something that we care about in education? So if you know anything about developmental psychology and social psychology, there's a lot of work showing that joint attention is a central mechanism for people to communicate and coordinate their action and their attention. For example, if you look at young children, it's a precursor for language learning. You have young children pointing at a thing, and then the caregiver sort of follows the pointer, identifies the objects, and names it. And that's how children start to learn words. It turns out that adults engage in a similar process, but instead of learning words, we learn how others perceive and think about the world. This is a process known as grounding in communication. Basically, people are trying to build a common ground to make sure that they're talking about the same thing and that they're on the same page. In collaborative learning, researchers go slightly beyond this concept of grounding, and they talk about how people build a shared problem space. It's basically a space where people try to build an understanding of the concepts that they're learning. It's a more dynamic space because people don't know what they're talking about, they're learning about it. So they have to constantly update the person they're working with to make sure that they're on the same page. And so for all of those processes, joint attention and proxy for it, joint visual attention plays a central role. So what you can do is to capture this concept using dual eye trackers. And in my lab, we're more interested in people working in physical spaces, working with each other, not really spending their time in front of a computer screen. So we use mobile eye trackers a lot, which look like glasses that have different cameras that can capture where your eyes are looking at. So it's not trivial to get measures of joint visual attention from mobile eye trackers. So if you look at the raw data from, let's say, those two people working together, you can see that the gaze of this person, the X and Y coordinates, might be the same as this person, but they might not be looking at the same place. So you have to do some work to be able to map those gazes into the same place to get this measure of joint visual attention. So this is a special synchronization problem. There's also a problem of temporal synchronization. You might start eye trackers at slightly different times, but you have to make sure that they are properly synchronized so that your time data makes sense. So for the temporal synchronization, what you can do is basically do a visual hand clap. So what we do is usually at the beginning of the task, we show them a unique fiducial marker, and then at the end of the task, we do the same thing with a different fiducial marker. And this way you can sort of trim the data by using computer vision algorithms and detect when those fiducial markers are shown. For the spatial synchronization, what we do is to detect the location of the fiducial markers on different AOIs. So you can see here that in that scene, we have a bunch of those QR codes everywhere. You can use a computer vision algorithm to detect where they are. In this case, we're actually using one that was developed in Pierre's lab. And by connecting those points and knowing where those shared set of points are, you can actually map the gaze into this common image here. And so when those 2 points are in the same place, you can define the threshold, and if those gaze points are in the same threshold, you can decide that this counts as joint visual attention. So you can run that for an entire episode, and you can do that for every frame of the video, and you can see here those two gazes sort of moving around together and turning red when there is some joint visual attention. So that's the basic idea, and that's something we've used in different studies. Now, what can you say with the data? You've done all that work. The first time I actually did this work of connecting that data, I think it took me an entire summer to generate that video and make it work. So, for example, in this task that we had 2 people working on programming a robot. So they were using this block-based environment on the computer here, and we give them progressively harder mazes to solve. So they had to program the robot to navigate the maze and reach the end. Those people had no idea of programming. We gave them a quick crash course before the study to explain how the interface worked, and then they tackled those different challenges. We had different measures. We had measures of learning using a pre and a post test to measure computational thinking skills. We had measures of task performance, basically how well they solve those different mazes. And we also used a rating scheme to assess their quality of collaboration. This rating scheme has different subdimensions where a person watches the video, gives a score to different episodes, and then you can aggregate them together to get an overall score of collaboration. So this is what the joint visual attention data looks like. On the left, you can see a group that wasn't working very well together. You can see levels are pretty low. There's not a lot of variation in the data. And on the right side, you can see a group that did really well on the task, and there were a lot of exchanges. They were very engaged in the activity. And so if you sum it up to get a measure, the whole measure of how much people align their attention, we found here a significant correlation with their quality of collaboration, which was a good evidence that this was actually capturing what we're thinking would capture. And in particular, with this subdimension of collaboration called sustaining mutual understanding. And that's sort of akin to this idea of building a common ground, of making sure that we're on the same page when we're working together. We didn't find any correlations with learning gains, which sort of shows that there are limitations to this measure as well. It says something interesting about collaboration, about how people work together, but that's a proxy that's a little too far from actual learning gains. We replicated this in different studies. This is actually using the tangible interface that Pierre talked about earlier. We had a study with apprentices in logistics, where in one condition they used those 3D physical shelves, and in the other one they used paper shelves with the exact same system, but the interface was flat. And we did the same type of computer vision operation to detect moments of joint visual attention. So you can see here the perspective of those 2 people working together at the top, and you can see their gazes on the bottom, looking at different warehouse layouts, trying to analyze them and figure out which one was more effective according to different criteria. So in this study, we also found that levels of joint visual attention was significantly correlated with people's quality of collaboration using this rating scheme, and also the performance on the task. So the quality of basically the layouts that is designed at the end. As a quick side note, we also found that people had more moments of joint visual attention using the 3D interface compared to the 2D interface. And there's a little bit more of a discussion of this result in the paper, but it sort of shows that the environment also influences what you pay attention to and how well you can, have those hotspots to look at the same place at the same time. So great. We have a couple of measures that give us some ideas of how people work together. Those are results that a lot of people have found. This is not something that is necessarily very new. So we were trying to think of ways to go a bit beyond that. So how do you go just beyond these basic results that, great, joint visual attention seems to matter. So one thing that we did in a different study was to look at groups that had high levels of joint visual attention, but did poorly on the task or didn't learn very much. And what we found is that by looking at the eye tracking data, that those groups tended to have always the same person initiate moments of joint visual attention, so going to a location, and then the other person was always responding to it and joining that person at that location. In good groups, usually that responsibility was shared. Like one time I'm the one who's initiating a moment of joint visual attention, and the other time it's my partner is doing it. And basically, it shows that you can identify a type of a free rider effect of a person who's dominating the interaction and a person who is disengaged and sort of sitting back by looking at those eye tracking patterns. We also found that high-performing groups tend to engage in interactive discourse, meaning that they tend to build on each other's ideas. So you can extract a measure for that from the transcripts. And we found this to be correlated with joint visual attention as well. So it's starting to show that if you start to triangulate those different things, they sort of start to point at the same direction. And lastly, we found that high-performing groups also tend to cycle through states of low and high joint visual attention more than low-performing groups. And I want to expand on this result a little bit more here, showing you those two groups I showed you earlier. So if you look at the group on the left, you can see that the levels of joint visual attention tend to be flat. There's less variation compared to the group on the right. And basically, you can design a measure to capture this. And the intuition is that when the signal goes up, you count that as a cycle when it goes up and down, and then you can keep doing that over the entire interaction. We also included speech so that those moments were not just about people looking at the same place at the same time, but also people talking at the same time. Because we found that those moments tended to be moments of collaboration, meaning people interacting with each other, being engaged on the same tasks. And when those measures went down, those tended to be moments of cooperation, meaning people working in parallel, not really interacting with each other, maybe being focused on the task, maybe not. So compared to a simple measure of joint visual attention, those are the subdimensions of the rating scheme I was talking about. This is the overall quality of collaboration. It's pretty small, sorry. You find some significant relationships, but not with learning. But if you use this measure of cycles of low and high joint visual attention, you find much stronger correlations, and you actually find correlations with learning gains. So it sort of shows that it's not just about aligning your attention, it's also about how many times do you iterate building the shared problem space. And that this kind of measure maybe can offer a proxy for this kind of interaction. We have lengthy qualitative analysis to sort of put more meat on those results in the paper that I invite you to look at if that's interesting to you. So that was the first part. This was showing you that, all right, with dual eye tracking, we can capture this idea of joint visual attention that says something interesting about group collaboration, and you can take advantage of the time series nature of the data to develop more interesting measures that go beyond this simple measure. Great. What do you do with this? How can you actually use those results to help students do a better job of working together? So in the second part, I wanted to talk about an invention that we've been working on for quite a bit of time called the shared gaze visualization. This is an example of a setup where you have two people working together and they're communicating with a microphone. We have eye trackers tracking their gaze, and we're basically showing the gaze of one person on the screen of the other person and vice versa. So it means that I can see where my partner is paying attention to, what they're looking at. And even before they say something, I sort of already know what they're going to say because I know what they're paying attention to. Here's an example of one of our RAs who was testing one of those systems. So you can see his gaze on the right side, but let's say I'm working on this laptop next to him. I could see his gaze move on the screen and I could follow his attentional processes. This is a similar video where two people are working on a physics task, understanding reflection. So on the left side, you could see this would be like a researcher dashboard where you can see the two gazes dance together and then go back and forth. And on the right side, let's say I'm working with Daniel, I could see Daniel's gaze in green, and I could see how he's trying to make sense of that visual material. We actually did a literature review with a colleague of mine, Sarah D'Angelo, on the benefits of shared gaze visualization. And this was one of the outputs where we basically surveyed the entire literature, trying to identify what were benefits that were cited by researchers. I'm just going to mention a few of them. So like I said, it can help you anticipate other people's intention because you know where they're looking at. It can disambiguate utterances with multiple meanings. So for example, if I'm talking about a diagram in the previous video, you're not going to know which diagram I'm talking about because there are several ones. But if you can see my gaze at the same time, you know that I'm talking about that one specific diagram. And so that can help reduce misunderstanding and confusion. It increases group awareness, obviously, because at all time I know what you're doing. I know that you're not off task. I know that you're not just playing on your phone. I know that you're also focused on the task that we have to do. It facilitates dyadic referencing because you can now point with your gaze, right? Instead of using your finger, you can just point at things just by looking at it, and so on and so forth. So we use this in one study where we had two students work together. Their goal was to learn about the human visual system. Basically, you had to analyze the set of contrasting cases, telling you how the brain processes visual information. And the idea is that the left side of your brain processes the right side of your visual field and vice versa. And in the back of your brain, in the optic radiations, the upper part of the optic radiations process the lower part of your visual field and vice versa. And so they had different lesions on those diagrams with different potential effects on the visual field, and they had to figure out which one matched which lesion. We also gave them a quick lecture afterwards to tell them how things actually worked. But the point is that when we look at the eye tracking data, not surprisingly, there was more joint visual attention for the group where they could see the gaze of their partner in real time compared to those who couldn't. It's not surprising because you have this like green bubble moving on the screen, so your gaze is going to be attracted to it. But interestingly, we found differences in their quality of collaboration and again on those sub-dimensions of sustaining mutual understanding. And we also found a difference for reaching a consensus. So it helped them sort of talk about the material, make sure that they understood each other, and then progress towards a solution. We're pretty excited because we also found differences in learning gains. So students who could see the gaze of their partner also learned more on the pre and post tests. And we looked a little bit deeper at the data, and we were able to classify each person in those groups as being either the leader of the interaction or the follower. So the leader was the person who was talking the most, making important decisions, deciding what they were going to talk about next, how they were going to go about the task. And the leader was the person who was a little bit more passive. We found this interaction effect where for people who could see the gaze of each other, there was no difference between the leader and the follower. For the leader in the no gaze group, this was not different from people who saw the gaze, but the follower who couldn't see the gaze of their partner tended to score lower. And that suggests that if you can see the gaze of the person you're talking to and the person is talking a lot, it's easier for you to follow the thought process of that person. If you don't see the gaze, you're going to be more likely to be confused, to not follow along, and at some point to be disengaged from the interaction. So that was for a student-student interaction. This is something that has been done in a bunch of different studies, but there are not a lot of studies where people have looked at teacher-student interaction. So using the same type of intervention, but displaying the gaze of a teacher or a student as they're learning and teaching in a setting. So we had a study here where a teacher was teaching the student how to program a microcontroller. This is the teacher's point of view. The teacher had a handout that they could follow if they wanted to. And this is the gaze in the eye tracking data. This is the student point of view. And you can see that the student has a laptop here. And the student can see the gaze of the teacher on the laptop. So they see a first-person perspective of the teacher, and they can also see these dots move around, indicating what the teacher was looking at. This is the student gaze. You can't really see very well, but basically the teacher could also see the gaze of the student on the laptop on the side. So they could monitor each other. They could see what each other was paying attention to using this shared gaze visualization. We had 3 conditions in this study. The gaze one is the one I just told you about. There was a head-mounted camera condition, which was the same as the gaze condition, except that we didn't show them the gaze circle. And then there was a webcam condition, which was basically just a Zoom session where they could see each other face-to-face. This was a pretty typical study with a pre-test. There was a warm-up task. There was an instruction phase where the teacher was teaching basic concepts, and then a practice phase that was student-led, where the student was solving different challenges, and the teacher could jump in to help him or her, or the student could ask for help. And then we had a post-test for the learner, and at the same time, the teacher was filling the same post-test, but trying to guess how well the student would do on those questions. So it's trying to predict the learning gains of the students. Here's just a quick video of the interaction. This is just showing fixations, but you can see how the teacher on the left side is sort of going back and forth between explaining the code and then looking at what the student is doing, and there's this back and forth monitoring to make sure that the student is following along. And you can imagine that in the Zoom condition, you can't really do that. You just explain things, you hope that the student is following along, but you don't really know what's going on. So we found that learning gains were actually the highest in the gaze condition compared to the webcam and the first-person perspective. And we found that students were a lot less offline when instructors were looking over their shoulders. Instructors were more engaged. They're doing more of this monitoring I was talking about. And interestingly, we found that low-achieving students seem to benefit the most. So students who did poorly on the pre-test, they seem to gain the most from this. We also found that there were few people who expressed concerns, who felt stressed out that there was so much data being shared about them, that the teacher could see their gaze at all time, and that they felt like there was always someone who was looking over the shoulder and sort of spying on them, which I think is a really important and interesting result that raises important questions of data privacy and maybe designing interfaces to let students disable that information or the gaze information that they're providing if they don't feel comfortable doing that. So there are interesting design and data privacy questions around this. We also found that the instructors were able to better predict the post-test scores with the gaze visualization. So they felt like they were better able to monitor what the student was doing and also help them give better feedback. Because they could see when students were making mistakes, if they were developing misconceptions, if they were getting stuck, if they were getting confused about a concept, and they could jump in to provide, just-in-time explanations. In the webcam condition, they're not doing all of that because they didn't know what the student was doing. So they tended to be more disengaged and just wait for questions because they could only see the student's face. Maybe they could guess something from facial expressions, but they couldn't really know if there was an issue or not. Quickly, we also looked at the eye tracking data, doing the same type of remapping that I told you about earlier. We had a slightly more complex common image because we had so many spreadsheets, instruction sheets that the instructor and the student were looking at. And I'm just going to show you one finding. So you can see here at the top, this is the instruction phase that was led by the teacher. This is the practice phase that was led by the students. With the student learning gains and the prediction of the teacher. I'm just going to show you results for joint visual attention. And we found that there was a significant correlation with learning gains during the instruction phase. And I think that indicates that the student was actually paying attention to the teacher's explanations because they're focusing on the same things. And that was predictive of learning. In the practice phase, joint visual attention was significantly correlated with the predictions of the teacher. And I think that shows that the teacher, if they were monitoring what the student was doing, if they're following their gaze, trying to guess what they were working on, then they were better able to predict what kind of struggles they had and how well or poorly they would do on the test. So that shows that this can be helpful not just for the student, but also for the teacher if they need to do some remediation for the students. So a couple of implications. Like I said, there's very little research on the effect of this kind of intervention on online teaching or tutoring, especially involving physical objects, not just 2D material on a computer screen. And those findings seem to suggest that this can help. This can help in those kinds of tutoring situations to help people better communicate and better understand what the other person is struggling with. And I think potentially in the next decade, this can have implications for the design of online teaching experiences because we're going to see a lot of new kinds of spaces emerge for teaching and learning. And a lot of the devices that allow for those experiences are starting to have eye tracking capabilities. So obviously you have laptops and smartphones that can do eye tracking, but there are a lot of AR and VR headsets that do eye tracking as well. The Apple Vision Pro does eye tracking. So there might be interesting applications in those kinds of spaces in the future of using shared gaze visualizations. All right, so now the second part showing how we can use that data in real time in actual settings to help teachers and students. In the last part, I want to talk about future work, some next steps that we're thinking about of how we can use multimodal data in general more effectively in education. The first thing I wanted to talk about is how do we get rid of those, bulky, intrusive eye trackers? Because we can't really use that in a classroom. That would be distracting, they're too expensive. It's just too much work to make this work. And so one direction that we're following is using computer vision algorithms that do gaze inference. So this is an example of one of them. It's called L2CS, where basically you just need a video recording, you pass this through the algorithm, and as an output, you get 3D vectors for the orientation of the gaze of each person that's detected on the video. And so using that, you can just use simple video recordings. You don't need eye trackers. It's not as accurate, obviously, and it's a bit more difficult to make sense of, but you get some measures of attention. So we're currently implementing this into a makerspace type of environment. This is the makerspace we have in our school. The makerspace has 8 cameras that capture what's going on in the space. We extract pose data from those cameras, and we then reconstruct them into 3D poses. And we're also using gaze detection algorithms to infer what students are paying attention to. So on the video, I don't know if you can see the lines in front of people. This is basically the 3D data that was mapped into the floor plan of the makerspace. You can see those two students working together. Those two, there's someone working on laser cutter here, and there's one student walking around the space here. And you can see here, those lines of sight turn red when there's some joint visual attention going on between those students. They're working together on this laptop. And you can see the students, going next to them and observing what they're doing. So we have collected a lot of data over an entire semester in that space. We're currently analyzing it, trying to figure out if there are interesting things that we can get out of that data. But I think it's promising, especially in terms of capturing those kinds of observational learning experiences where people are learning together, but also learning by observing other people work in the space. So when I have news, I'll let you know if we have interesting findings. So that was one future next direction. Another next direction is how do we help people do this work, but with other types of data? Let's say people have a lot of data that they're collecting in a learning environment. How do they make sense of it? How do they know what kind of features or measures might be useful for them? So it's not a trivial question because you can go on Google Scholar, get a bunch of papers, but a lot of the results are going to feel, anecdotal. They're generated on a small sample size. They're not replicated. They might be context dependent. They're computed in different ways. They might be specific to a population. They might be popular because they're easy to generate, and so on. So we don't have very good overviews of what's going on in that space. And so last year we published a paper where we did a review on this field of multimodal collaboration analytics. Basically, what are interesting multimodal indicators of collaboration using sensor-generated data or automatically generated data? And as part of this paper, we also built this website that you can access at mmca.gsc.harvard.edu, where we have, it's a first draft of a visualization, but we basically decomposing collaboration into properties, products, and conditions. This is based on existing work. And we have all of the different measures that people have used in, I think, 70 papers or so in terms of gaze, body, verbal data, and there are some sub-dimensions here. What you can do is, for example, if you're interested in body data, you can click on this. It's going to show you all the different measures that people have used. And if you're interested in head-body movement, for example, you can click here, and that's going to open a Google Scholar page where you can actually go have a look at the paper and see how they implemented that measure. You can do the same thing with, for example, if you're interested in coordination, you can see all the metrics that people have used using different modalities. You can click on them as well. And you can also click between the relationship between metrics and outcomes. So here, for example, you can see all the performance outcomes that have been used and all the gaze metrics that have been related to those outcomes. So this is the very first step towards making it easier for people to orient themselves in that field. We're currently expanding this to include another decade worth of data. I think we have 150 papers now that we're analyzing. But we really feel like this kind of platform can help, inform feature engineering, because otherwise, you just use your gut feelings or a few papers, and it's not really based on actual evidence. It can also help identify underexplored areas of research. For example, if you look at the visualization, you can see that the affective side of things in collaboration is really underexplored using those kinds of methods. Can help us build more complex models of collaboration and so on. So as a next step, we're also improving the visualization so that you can, for example, use filters. If you're interested in children, you can filter the papers that only dealt with children. Or if you're interested in classrooms or open-ended learning environments, you could filter out those results and see how the findings that we have applied to the context that you're interested in. And finally, The third work in progress that we have is putting together some kind of repository of tools that people can use. It's a big problem in multimodal data collection because basically either you have to buy very expensive sensors like eye trackers that cost thousands of dollars, or you need a very very strong technical know-how. You basically need a CS degree to get the data, make sense of it, analyze it, and so on. So in this other project, we have built a website that makes it easier to collect multimodal information. And as long as you have a browser, you can use it and collect data. It's accessible to anyone at mmla.gsc.harvard.edu. And if you click on it and you go to the tools category, we have a lot of models where you can do pose detection, you can do hand detection, emotion recognition, you can do heart rate detection as well. A lot of those models are in JavaScript, so they can be run in the browser. You don't need to install anything. You can just use it as they are. We also have a bunch of Python models as Colab notebooks. I'm just going to show you one example of a model. This is a holistic model where you can do pose detection, hand pose detection, and facial landmark detection all at once. It's using my phone's camera. So, it detects all of those key points. And the only thing you have to do to collect the data is press on the record button here. You can tag events. Let's say I'm starting, an activity now. I can tag the beginning. Now I can tag again to show the end. I can stop data collection. I get a summary of the data that's been collected. And then you can just download the predictions and the video that are going to look like a CSV file. I don't know if that's going to be shared, probably not. Yeah, basically you get the CSV file with all of the data where all of those key points have been detected on every frame of the video. So I've been using this for a data science course for quantified self projects where students collect data on themselves or other people around them. And then they can actually collect big data sets pretty quickly. And those are rich data sets. They're really interesting to analyze. And they're really good examples for data science projects. So our goal with this is to create we call it a low threshold, high ceiling type of toolkit, where anyone can go onto that website, collect data, try to make sense of it. But it's also high ceiling, meaning that you can do very complex projects as well. One next step is that we're also working on including computational notebooks so that you don't have just the tools to collect the data, you also have tools to transform the data into interesting features. So let's say you're collecting eye tracking data with this website, you could have computational notebooks that help you compute measures of longitudinal attention, for example. All right, so in conclusion, a couple of takeaways. So like I said, among all the work that we've done, all the modalities that you can work with, we found that theory-based constructs tend to be more helpful. So for us, it was very productive to start with this theory about joint visual attention and try to use that to implement interesting measures. And also use that to design interventions to support, in this case, collaboration between students and students or students and teachers. And some promising work for us is to try to use those results, but in more ecological settings, right? Try to go beyond those lab studies where you can control everything, but try to do the same type of work in, for example, open-ended environments like makerspaces, where you don't control anything. It's so messy, but at least, it's a real-world learning environment. And I think it's also interesting to try to come up with better tools to help people capture and make sense of their data, so that we're not reinventing the wheel every time we're building a system. We actually have prior work that we can look at, and we can use that information to inform our decisions. All right, I'm going to stop here. Thank you for your attention, and happy to take any questions.
Thank you so much for this super interesting presentation. I don't know if there are some, please.
Yeah.
Hello, thank you very much. It was a very interesting presentation. I discovered the report I was very early. I have one question and one more general common brainstorming thing. So yesterday, I don't know if you were here, but we had a very nice talk about the combination of statistics and deep learning and all the potential possibilities that this new explainable AI will offer to the science. So my question is, do you use any AI to explore the potential relationships between gaze motion and the effect on learning? Because you said also something interesting. Sometimes you have a high visual attention measure, that it doesn't necessarily mean that your subject is learning. How could AI help us to explore this different phenomenon? And if yes, how do you think can we deal with this paradoxal observations? I don't know if I'm clear.
Yeah, I think I got your question. Yeah, thank you. I think that's a really interesting question. I think you could definitely use that data in AI systems. There are actually people who've used eye tracking data in interactive tutoring systems, where you have an AI tutor who's helping a student. And they could use eye tracking data, for example, to detect if the student was paying attention to the hints that were being displayed. And if not, then you can prompt the student to be like, hey, there's really useful information here. You should pay attention to this. So I think, yeah, I think there are interesting applications. It's not exactly my field. I don't develop AI applications, but I think it's an interesting direction to follow. I'm trying to think what else could be done that could be helpful. And also, again, I think an important consideration to keep in mind is to make sure that the students don't feel like they're being spied on, and that you respect their privacy. So I think in an environment where you're providing this as formative feedback, where the goal is to help them learn, that can work if you frame it in the appropriate way. But if you have any summative measure, if anything related to this environment, related to grades or summative feedback, I think that becomes much more tricky. So there's a lot of work that has to be done by the people who develop the applications and the teacher to contextualize why they're using it and why the data might be helpful for their learning. Sorry, I sort of went on a tangent. Yeah.
Thank you for the very interesting talk. So I have a couple of questions. I'll start with one. So I think it was in part 1, slide 12.
That's very precise.
Yeah, I noted the slide because it's easier. But over there, I think you talked about students.
This one?
Mm-hmm. So I was wondering, like, when you say quality of collaboration, so how were you measuring that? Was it like a subjective metric? Was it coding? Because
yeah, go ahead.
Yeah, because the question that I'm really interested to ask is that how do you disentangle quality of collaboration, the measurement of quality of collaboration from learning gain? Because I've personally worked on modeling engagement in collaborative learning environments. And I think it's a very hard problem to distinguish between engagement that is conducive to learning versus, something that apparently might look like good engagement, but it isn't conducive to learning.
Yeah, so we're using this rating scheme from the field of computer-supported collaborative learning. And basically, you have those 9 sub-dimensions, for example, how well people sustain mutual understanding, how well they manage dialogue, how well they pool information, and so on. And you have 2 raters who judge, the quality of their interactions based on the video recording. And they give them a score between, I think, -2 and +2. So it gives you a rough proxy for how well they're doing on those dimensions. Obviously, you have to do a good job of training people so that you have good inter-judge reliability. And it's a somewhat subjective measure, but I think that's the best that we have right now, because you need, contextual information from the raters about the task, what people are doing. And yeah, I don't know if there are better ways of doing this, but this is something that's been used in the literature a lot, and that seems to work pretty well.
But did you think about at some point during the future to also look at like data-driven ways of surfacing maybe sets of behaviors that could link with higher learning gaming groups, and then to see that if those groups were also rated higher on collaboration by this rating scheme?
Yeah. So this is part of the work that I've mentioned here as well. So there is this idea from theory from CSCL that transactive discourse is good for group learning, for example, right? It's not just about being engaged, but it's also about building on each other's contributions so that, you make progress, or about arguing about what the other person is proposing. So yes, we're trying to use different measures. And again, I think this idea of triangulation is important. So if you have several measures that point in the same direction, for example, your transcript are telling you that people are having good transactive discourse, and you find more visual attention, you have this rating scheme that also agrees, then you can be more confident that you're actually assessing the quality of their collaboration.
I will leave my next question.
So we have a lot. Kelly, last question.
Yeah, I agree with Javi that you made so hard to pick one or two questions to be made, because it was very, very rich talk. So thank you very much. But I think I can summarize my questions in one point. That is, it feels to me that you prevented many problems by restricting your activities. So and I would like you to comment a bit before all these applications. So when you're designing the activities and when you are somehow, trying to find the best way of using your software or your hardware, but you have to think all the limitations that this could bring. And if you have any tips, they are more than welcome. We have a big community here that is also trying to deal with all these things. So can you please comment on the designing and activity design and how to avoid this process?
Yeah, that's a great question. And I think in educational research, there's actually a big debate between open-ended learning activities or discovery-based learning, or all those approaches where there's a lot of agency that's put on students, but it's really difficult to know where they're going because they can go in 1,000 different directions. And that's the kind of thing that we prefer. We like giving this kind of freedom to students. And on the other hand, there are more, well-structured activities where you know exactly what are the right steps that students need to take at each point in time. That's more boring. That's more about learning procedural knowledge or some conceptual knowledge in some cases. And so I think the trick is to find something that's a little bit in between. And one trick that I've used over the years is to find pedagogical strategies that people have developed in the learning sciences and try to reuse them. So, for example, in the first study about the shared gaze visualization, using those contrasting cases, this is actually part of a pedagogical strategy called preparation for future learning. It's pretty similar to productive failure. That's something that you're familiar with. But basically, you give an open-ended task first to students so that they can struggle with those ideas. They can figure out what they don't know. They can come up with predictions, like Pierre was saying. They have rich discussions about how things might work. And then after you've done that, where they've gone in 1,000 directions, you actually give them a small lecture to explain to them how things work. And if you've asked yourself a lot of questions, then the lecture is going to make a lot of sense to you. If you only hear the lecture, you're going to be like, oh yeah, it's obvious, I know that. And then you take the test and you realize, oh no, actually, I don't know those things very well. So that's an example, for example, strategy that works for designing studies where you have a little bit of both.